Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at section 2.2 in our text titled Key Facts About Complex Numbers. So let me begin. We say a complex number z is equal to a plus ib, where a and b are, we say they're in the real numbers, so they could be pi, or they could be 3, they could even be something like -2. And we say that the real part of z is a, and we say that the imaginary part of z is the b. Okay, so let's take a look at this. So when I represent a complex number, I represent it in the complex plane. Well, we do that with 2 dimensions. So let's try this. I'm going to draw this. Okay. On the horizontal axis, we map the real component, and on the vertical axis, we plot the imaginary component. So for example, here I have the number z is a plus ib. So I would come out on the real axis to a, and then I would go up on the imaginary axis to b. And then where those 2 numbers meet, that right there, that didn't really line up very well, did it? That would be the number z. Okay, so let's write that. So this is the number z equals a plus ib. And when it's written this way, we say this is its rectangular form. This is the rectangular form of z. Well, that kind of implies that there might be another form. And there is another form. It's called the polar form, and we're going to see that in a minute. Now, before we go into the polar form, we say that the length of z, we call it the length of z. Let me go back to my white. The length of z z, and we write it like this with little absolute value bars around it. Length of z is equal to, it's also referenced by like a lowercase r or maybe a capital R. We'll see why shortly. Length of z equals r. Well, it's just found using the Pythagorean theorem like you might expect. So it's the right side, so that's a squared, plus the vertical side of our triangle, that's the b squared. You take the square root of that, and what do you have? You have the length, or the modulus, or it's also called, or the modulus of z. Now, the complex numbers often come in pairs. For example, if you've ever solved the quadratic equation and come up with a complex solution, you normally had minus b plus or minus I times some square root. Well, what is that plus or the minus part? That minus part is actually called the complex conjugate of z. And it comes up so often that we need to make note of it. So the complex conjugate of z, it's written is z with a bar over it, and it's all we do is we change the sign on the imaginary component. So it'd be a minus I times b. And if I went to graph this, let's go out and graph this, and we'll graph this in this pretty kind of pinkish color here. I think that should show up well. If I graph this, if I've gone up b, I would come down to b, and then I would go over to a. And that would be my complex conjugate. Okay, now let's do a little bit more with this. When we multiply complex numbers, for example, if I take z and I multiply it by its complex conjugate, well, that means I take a plus I times b times a minus, actually before I do that I should add complex numbers. So how do we add complex numbers? Quick review, add complex. Add complex numbers. All right, so we already have z, that's a plus ib. What if I have another one, s, that's equal to x plus I times y? Let's add these. So if I want to add z plus s, well, that's going to be a plus ib plus, then I'm going to have my s. Well, s is x plus I y. And when we add these, we add the real components. So I'm going to put them in parentheses just so it's easier to see. I would have an a plus x plus, and then I'd have my imaginary component I, which would have a b plus y. So that's how I would add. Now, with that, we can now multiply. Let's try this. Let's take and let's multiply z with its complex conjugate. In other words, we're going to take a plus ib, and we're going to multiply it by a minus ib. That's going to be a times a. That's going to pick up an a squared. Then we're going to have a plus, I'm sorry, not a plus, a minus a ib. We're going to have a plus a I b, and then we're going to pick up a minus I squared b squared. So I'll write that, minus I squared b squared. Now a couple things happen here. First off, we have opposite terms right there, so those are just 0. And I squared is -1. So this really just becomes a squared plus b squared. In other words, look at this. Z times its complex conjugate is the same as its modulus squared. There we go. So there's another interesting piece. Now, I alluded earlier to possible other forms. Let's take a look. The other form of a number, of a complex number, is called its polar form. Polar form. So, what we do to map our polar form is, well, notice this is always our reference. Our reference is always from the positive real axis. So maybe z is some angle here, we'll call it alpha. And notice this then. Well, what does that tell me? If I have that's alpha and I have z, I've drawn it out as a right triangle, I can also say that the cosine of alpha is equal to the adjacent side, that's a, over the modulus r. But I could multiply both sides by r, and I could write this as r times the cosine of theta is equal to a. Similarly, we could say that the sine of alpha, well, that is equal to the opposite over the modulus, or the hypotenuse. And if I multiply both sides by r, I could say that r times the sine of alpha is equal to b. Now let's substitute this in. This says then that z in the rectangular form is a plus ib. Well, what did we say that a is? We said that a is r cosine of theta plus I times b, but b is right above. That's r sine, oops, not theta, that should be an alpha. Cosine of alpha plus I r sine of alpha. But if I factor out the r's, this is going to be r times cosine of alpha plus I times the sine of alpha. And you may already know the answer because this is the key piece. This is the key piece. This cosine alpha plus I sine alpha is very famous. This is the exponential or polar form of a complex number. And so we write that as the modulus r times e to the I alpha. There we have it. Now, look at this. This brings up an interesting point. We can write the complex conjugate this way as well. So the complex conjugate, z bar, well, it has the same modulus, of course, so that's going to be r. And then this time, though, what is the difference here? Well, now alpha is not positive alpha, it's minus alpha. So this is r, e, I to the minus, I'll write it this way. R, E, I to the minus alpha, and you'll more commonly just write it as R, E to the minus I alpha. Now, up above, earlier we just said up above here, let me lead you back here. If we go up above, what did we say about R? We said that if you multiply a complex number times its complex conjugate, that you should get r squared. That's what we found. Let's see if that's true now using the polar form. So if I take the polar form, this would be z times its complex conjugate. Well, that's r. I'll put it in parentheses for clarity. This is r e to the I alpha times r e to the minus I alpha. But remember, when you're multiplying exponentials, you'd multiply the r's, so that's going to be r times r, or r squared. And then since we're multiplying the exponentials, the beauty of multiplication of complex numbers in their polar form is all you do is add the exponent. So this becomes e to the I alpha minus I alpha. Oh, but those are opposites. In other words, this is r squared times e to the 0. E to the 0 is 1, and this is r squared. And r squared is exactly what we suspected from up above. And that is the basics of using complex numbers. I think we'll stop there. Hope that helps, and thanks for watching.